All right, so now what we want to do is we want to start talking about this part. Again, it's a plate welded on a pipe with a hole punched in it. And now we're going to be integrating this in with another part. Okay, so let's say, for example, you have this piece. You're designing up a machine, and this is one of the pieces you're going to be using in your machine, and you want to fit this into, let's say, a larger plate. Okay, so in this particular case, let's pretend for a moment. Let's draw this plate right here. So you have some sort of plate design. This piece, you want it to set into an inside hole, if you will. And so we're going to draw this. Let's pretend that this little box inside is a hole, and this pipe and plate, sit into that hole. Okay, so for the sake of this illustration, now we have parts that are mating or meeting together. So when it's one part, it's called an allowance. Now multiple parts, with one part, it's called a tolerance, how much wiggle room you have. Now we're getting into part allowances, when parts are meeting up, how they interact with each other. So a moment ago, I mentioned in the previous video that sometimes you might specify an upper or lower limit. All right, so in this particular case, these three dimensions have the same range. They're specified differently. This one has a standard plus minus. This one has an upper lower limit. This one here has the upper limit set where you cannot go any larger, but you can go below it. So 4.005, that's the max that it's allowed, plus nothing, so 0.000. So it cannot go any higher than that, but here it can go below that, up to 0.010. The reason you may specify that sometimes is because of how it mates with another part. So let's say, for example, that in this scenario, we have this hole here, and this hole now needs to be wide enough to accept this plate in it. Not enough where it's going to wiggle, but it has to have what's called a slip fit. So a slip fit means that there's at least a couple of thousandths, maybe let's say for this analogy 1,000th, 0.001 allowance in between the smallest this hole can be and the largest this plate can be. So in this particular case, this plate may be manufactured up to the largest amount, 4.005. And so we're going to add, let's say, 1,000th to that and say that this plate right here, and just for the sake of room, I'm going to kind of draw this out to the side here, is now 4.006. So this hole now is going to be the smallest it can be at 4.006 to compensate for this plate up here at 4.005, the largest that it can be. So in this particular case, we're also going to set tolerance limits. Okay? In this case, we do not want the hole to be any smaller, and so because of that, if it was smaller, this 4.005 plate would not fit in there. So instead, we're going to set the lower limit at 0. So minus 0.000. Just like up here we set the plus limit, it can't be any bigger than this. Here we're setting the hole limit, it can't be any smaller than this to ensure that that plate can fit in there. Okay, let's say that we're using the same tolerance zone here, so plus or minus 5 thousandths, that's 10 thousandths total, or 0.010. So in this case, the lower limit is nothing, the upper limit is plus 0.010. So keeping these tolerances the same range, okay, 3 place decimals. Now, this part is ensured the biggest it's going to be is 4.005. It can be a little smaller, but not any bigger. This hole, the smallest it can be is 4.006. It can be bigger, but it can't be any smaller. This now ensures on the engineering blueprint that so long as that part is manufactured in the tolerance zone, this plate will always fit in there, regardless of who makes the plate with the hole, regardless of who makes the plate with the pipe. So we have now covered why you might set an upper or a lower limit, especially with regards to mating parts. So now we're going to talk about how these interact and how you calculate up your tolerance range. Okay? So what I'm going to do here is just simply walking through the process. So if I look at, let's say for example, well, let me change colors here for just a minute. To keep these colors consistent, we have a plate, and I'm going to draw these holes kind of distorted so you can see what's going on here. So in this particular case, it's going to be a smaller hole, and the plate here is going to have a much larger hole cut. Okay? So now it's showing the lower limit, which is the smaller one, and it's showing the upper limit, which is the bigger tolerance. In the same way, we're going to also show this part with the upper and lower limits here. Now in this particular case, we'll draw this in blue. And so the biggest this part can be in the smallest hole, we'll draw this that way. And I'm going to do the opposite, the smallest hole in the smallest part in the biggest hole. So in this case, I'll draw that small. Anytime you're doing this, if you're thinking about this for a quiz or a test, if you're calculating up tolerances, if you're calculating up what's called MMC and LMC, which we'll talk about in just a minute, maximum material condition or least material condition, if you're calculating any of these up, it's a good rule of thumb in your mind as you're thinking about it. If you're comparing two holes, do not compare two holes that look about the same and one's barely smaller. You'll still be confused. Instead, think about it in terms of you got a hole this big and you got a hole this big as you're thinking through this part of what's an MMC, what's an LMC, how do these mate up. Okay, so just kind of keep that in the back of your mind as you're thinking through this process. So now what we're going to do is we're going to calculate up our tolerance zones here. Okay, so with the scenario that we have the biggest part for the plate and the smallest hole size that plate's going to fit into. What I'm going to do is I'm going to specify the hole, which is the smallest it can be is 4.006. So that's the smallest the hole can be. Now we want to do the largest the part can be, which is right over here. And so our part is 4.005. If I subtract those out, 4.006 minus 4.005, what we are left with is 0.001. Okay? What that means is the minimum allowance or tolerance between one part and another, if these parts are made within spec and they meet specification, at the smallest hole and at the largest plate, we're going to have at least 1,000th of an inch, 0.001. Okay? We're going to now do the opposite on the other side. So we'll keep the same hole. This time it's the biggest hole. In this case, the hole cannot be any smaller than 0.0000. It can go up 0.010. So the hole size now is 4.016. That's the largest the hole can be. And in this case with the part, the smallest this can be is 4.005 minus 0.010. Okay, so 10 thousandths here, which gives us 3,995. So if we subtract this out, 4.016 minus 3.995, we are left with 0.021. Okay, so this is now the maximum that the part can be. Okay, so now we have this tolerance range. This is the range that's set for the biggest to the smallest of how much wiggle room or slop the part's going to have inside of this square hole. In this particular case, if things are as tight as possible, we got 1,000th of clearance. If things are as loose as possible, we have 0.021, so 21 thousandths of clearance. A little bit more wiggle room at that end. Okay, so these are your upper and lower limits. Now, what we want to do is we want to talk about how this fits in. Sorry. So at this stage of the game, we've calculated up the tolerances for the part, for the square hole, how to find the upper lower limits.